So my name is David Vaughan. I'm going to talk about Biochar, which is a biochar being developed for the anaerobic digestion industry. So very little quickly on my background. This is much to tell you that I'm not a biochar or pyrolysis expert. I'm a biologist. So I work for the University of York in many different biological fields. I set up an anaerobic digestion facility at York University and was lead on AD research there. I left York University in 2019 to do some freelance work, and as we all know now, 2019 was the worst year to try and set up a business. I then joined Jennings towards the end of 2020 on a 4-month contract to do some industrial trial coordination, and I've been here nearly 3 years now, and I'm down looking at anaerobic digestion business development and some R&D work as well. So Jennings is a spin out from Edinburgh University, spun out in 2016, was started by Jan Mulmer, and it was looking to develop and produce sustainable carbon additives for biotechnological applications. They're focusing on anaerobic digestion and the wastewater treatment industry. I sometimes forget that some people might not know what anaerobic digestion is. It's basically the conversion of biomass, organic materials, into biogas, which can either be upgraded and put into the gas grid, or can be burnt to produce electricity, which then can also be put into the electricity grid. We're account managed by Scottish Enterprise. The beginning of this year, we managed to win £1 million worth of investment, which is going to allow us at the beginning of next year to set up our own full-scale production site, initially producing 400 tons of biochar, and then within another year to 18 months, looking at producing 1,000 tons. We have our own working here at the University of Edinburgh. We have our own research facility as well, so we can do working with in anaerobic digestion. We can look at batch test reactors, so looking at small scale, and then we can then scale those up to continuous test reactors. That is trying as best as you can at that scale to mimic what's going on in a full-scale anaerobic digestion facility. We also have, because anaerobic digestion is a very complex microbial soup, we can do metagenomic analysis as well, so we can look at how the biochar is interacting with the microbiology within the AD system and seeing how it changes that AD system over a period of time. And that's something we're going to try and look at a lot more in the future. So one of the stated aims for Biochar is to try to recover value from biomass. We initially was looking at paper and cardboard waste and other waste products. Unfortunately, when you start looking at waste products or things that are not on an Environment Agency's approved list, you start moving into being an incinerator rather than just a pyrolysis unit, and that brings with it a whole raft of legislation, which makes life a heck of a lot harder for a small company like ours. So we are looking initially at the materials that are on the approved list for the Environment Agency, so we can work with things like straw and maltings, but we are still looking at those waste products such as biosolids from wastewater treatment industry. That's something that's going to be very important over the next few years in the UK and probably Europe-wide as well. And we also had a look at screening waste, which is the rubbish that's taken off before wastewater goes through the wastewater process, and we were able to produce a biochar from the screening waste, which has similar characteristics to the Biochar product that we're producing from straw and paper, but has a slightly different morphological look to it. I'm not going to mention that much here. We have done a little bit of research on that, but it's something we're still working on. So we are looking with, I see a lot of you are sort of biochar experts, so you'll know more about this than I do, but we're looking at a material that has a large surface area mineral composition, which helps microbial colonization. We're looking for the microbes to actually colonize this material and be evenly distributed throughout the AD system. With an electrically conductive material, there is some evidence in the literature that suggests that direct interspecies electron transfer, which is electron transfer between microbes, either by contact or through electrically conductive material, may be one of the modes of action for biochar in the AD system. I think there's still quite a bit of work left to be done on that, and how much it actually contributes to any benefits we see, I think it still needs to be looked at. But what we do see the benefits with the biochar is an increase in biogas output, a reduced amount of foaming in the AD system. This is quite important for anaerobic digesters at an industrial scale, because foaming can be a big problem for them. Process stability, again, the less amount of troubleshooting that the industrial site needs to do, the better. For those sites that are running CHPs that maximize their energy output all the time, they want to reduce the cost of their feedstocks going in, because they pay for some of these feedstocks. They cost them quite a lot of money. So if you can get lower feedstock costs and the less feedstock that goes in the front end, you have a reduced amount of sludge coming out the back end, which then reduces the disposal costs of that. So the initial experiments were conducted in the lab. So we used these small scale continuous stirred tank reactors. These were developed by Jan again here at Jennings. They were using the wastewater treatment materials, so digestate and activated sludge from a local wastewater treatment reactor here in Scotland, and they ran it for 26 days at 36 degrees C. And what they saw was, after a period of stabilization, they then started to see that the reactors that had the biochar in it started to produce more methane. So they look at, on average, getting a 10% increase in methane yield and a 10% reduction in the sludge and chemical oxygen demand of that material coming out of the other end. So this was in the small scale, lab scale reactors, which are all very well controlled. Unfortunately, on a full scale site, the control is much, much less. So in order to know how this really works in anaerobic digestion properly, we needed to go to full scale industrial trials. And luckily we had a local AD site which was willing to let us put our material into their reactor. We did 2 trials initially. The first one was just a single large application of the biochar into the reactor and to see what would happen. And the second one was a much more controlled trial, which was using a large priming dose and then followed by daily doses after that. We have the facility to do a whole raft of analyses, which are important and very standard in the AD industry. This particular site operates with farm waste, distillery wastes, as in Scotland, and energy crops. And what we do is we provide the biochar in these fermentable, digestible bags. So basically what you do is just throw the bag into the feed hopper and then the machinery takes it through. It's a fairly standard way of putting additives into an AD site. So the first trial with a single application wasn't that successful, but that was largely because the site itself had a mechanical issue not related to the char input, and which meant that we really only were able to run the trial for a few days before it had to stop, before the data we were getting wasn't any use. But what we did see is that volatile fatty acids, these are intermediates in the methane production. So acetic acid and propionic acid are the most important ones. We saw quite a dramatic reduction in the levels of these in the early stages, which suggests something was happening. But obviously, because we weren't able to run the trial any longer than that, we weren't able to generate as much data as we would have liked. So we then went on to the second trial, which looked at the large priming dose followed by the smaller daily doses. The green bars obviously showed the methane output in meter cubed per ton organic matter going in, and the black line is the biochar addition. And over the course of the trial, we had an increase in the methane output, which was very encouraging for us. And going on with that acetic acid concentration, again, what we saw during the trial was that acetic acid concentration settled down to a very low level through most of the trial. There's always going to be ups and downs, but the amount of noise was much, much reduced. One of the other things that we needed to be careful of is digestate quality. So the digestate that comes out the other end, which is basically the digestive material, is primarily sent to land, and there is a quality protocol in the UK which you have to adhere to, which sets limits on various different parameters within the digestate, and one of those major parameters is heavy metal contamination. So we sent the material away to an independent lab to have it assessed, and what we found out was that even with the addition of the biochar, the digestate heavy metal contents in the digestate were either very negligibly affected or not affected at all, and this gives us a lot of confidence that our material would actually not affect the digestate quality and allow companies to get their what they call it, the PAS 110, which is the quality protocol in the UK, allowed them to get their certificate for spreading on land. And so if we, obviously we're looking at these industrial trials, we're looking at what are the benefits to a site like this. So this site operates a combined heat and power engine, so it maximizes that engine productivity all the time. So what it's looking to do is reduce the amount of feedstock going in. So if we can get an uplift of around about 10%, which is what we were getting at that time, we can make a feedstock saving to them of about £108,000 and a digestate disposal saving of £15,000. And obviously, if we can increase that uplift with increasing the dosage, we might be able to sort of save them even more money. These sites run on fairly tight margins, so these kind of savings are very significant to them. We did another 2 further trials on a biomethane site. So these are sites that upgrade their biogas and inject that biogas into the grid. These 2 sites were using very similar crops, although one of them was using chicken litter and whole beet and potato, but the major one was energy crops. The major input is energy crops. These 2 sites both had a similar setup where they had 2 primary tanks running in parallel, and we were able to add the biochar to one of the tanks. Unfortunately, the gas measured across the whole site, we weren't able to measure that gas production on individual tanks, which would have been ideal for us. We would have been able to, we've been able to sort of show an increased gas in that particular tank, but we were able to measure across the whole site. And I'll show you the results for one of those trials. So this is quite, both trials showed around about a 4% rise in biogas across the whole site, bearing in mind we're only treating half the material going in. Both sides also showed an increase in methane concentration, which is around about 2% increase in methane concentration. And also both sides showed a reduction in ammonia concentration. Ammonia is quite important in that it can be toxic at very high levels to the microbiology, and it can reduce productivity. This site, you can see that the black line is the amount of biochar going in. There was a break in the middle of about a month between two trials basically, but it was continuous because because of the hydraulic retention time within these tanks. It does take a few months for the biochar to wash out. And on the whole, we were seeing an increase in biochar, in methane concentration coming out of those sites. But what we can see here is oops, go back one, is the November 21 spike and the July 22 dip. And these are some of the issues that we come up with when working with biomethane sites. The July 22 dip was as a result of an increase in temperature. We had for the UK quite a warm July, and an increase in temperature of about 2 degrees. So you can stress the microbiology and you'll get a reduced amount of biochar coming out. What was the cause of the November spike? We don't know. But this leads us to some of the challenges that we have with industrial trials, and that the fact that we didn't have our own production facility at the time means that we had to outsource production. And because we had specific characteristics that we want for the biochar, it meant it was very difficult to actually get somebody to manufacture this product for us. And also we do our bagging by hand because we don't have a production facility or a bagging facility at the moment. So that's done by hand. So it's a very laborious process. So generating the tons of material that we need in order to run these trials is very difficult. So this means that the availability meant that the trial duration was shorter than we would like. We would like to run a year-long trial to take into account the ups and downs of the seasonal basis of AD sites, the breakdowns that occur. These sites are always having issues such as feeder breakdowns, engine breakdowns, stirrer breakdowns, and things like that. They're very temperamental sites, so we need a longer-term trial in order to accurately get the trends so that we can report them correctly. And also dosage. We have the limited supply means that the dosage can't be analysed, and the trials suggest that we were underdosing. So that what we want to do is get a longer term trials and be able to play with the dosage, and that's why our own production facility will help us to do that. So in summary, we have an additive derived from selected secondary biomasses for the time being. We will want to go into to wastes in the future. We've seen that this can strengthen the AD microflora through colonization with key microorganisms. There may be other mechanisms of activity in there, but we've yet to confirm those. We can enhance methane productivity capacity, but also the methane concentration. We've seen reduced ammonia. We have 3 full-scale trials that we've run. We've got more trials to go in 2023. We've got one with a wastewater treatment company. Because of our investment, we're now running consultancy as well, and we're looking to get our commercial production up and running in 2024. And this is the team, so we're only a small team. So Ed Craig is our CEO, he's been with us about 18 months. Lydia Shinovic, she is a business development director and also one of the co-founders. We've got Leah, that runs our research and innovation. Carolina is our lab manager. Lucy Chappell, she's doing an operations specialist, but she's also looking at various different feedstocks as well. So we can sort of expand our range of feedstocks. She's looked at about 25, I think, at the moment. I mentioned the bagging by hand. Daniel is the one that does all the dirty work, and Jan Mummer is still working with us, but only on a consultancy basis. Thank you very much.
Thank you, David. It was nice to see what's happening at Jennings. And also good to see that the biochar production will come up. So
yes, we're really waiting for that.
If anyone has questions, please write them into the chat. And the first question was from Kevisa. So I think you mentioned that the digestate is disposed on land. Couldn't it be used as a fertilizer?
Yes, it is. I mean, it goes to land, and it is used as a fertilizer. Most of it goes to farmland. So yeah, it's a very good nitrogen fertilizer. Actually, there are issues with it because it's readily available nitrogen. So we have issues with spreading too close to water courses. We are generally a wet country, so putting more water onto the land can be quite damaging to the soil structure at times as well. And obviously the biochar as well will go to land at the same time.
And the second question was, I think also something about more of the question is, have you ever tried to reuse the digestate to produce biomethane? I guess
some of that does happen. Some of it's recirculated, so you do get separation. So you get especially on farm waste sites where they've got a sort of more fibrous materials. Food waste doesn't work so well, but on farm waste sites where you've got 4 fibrous materials, you can separate the liquid and solid fractions out and put some of the solid fraction back in. Obviously, there's a much reduced energy potential in that, and you need to try and maximize the energy potential as much as possible.
And one question from myself, which I'm probably already talked about it. Is there any way to find out how much of your creature survives the AD process?
It's incredibly difficult. I mean, trying to sort of pick it out of there. We're not actually using a very large amount in there compared to the size of the tank. I mean, if you've got a kind of a tank that is 4,500 cubic meters, we're only sort of kind of 1 or 2 grams per cubic meter in total, I think, something like that, you know.
And do you know if you would get carbon credits for your biochar in AD?
Yes, we are sort of working quite heavily in the carbon credit market as well. So, you know, obviously we've been looking for the EBC certification. We think we can get carbon credits for our biochar, providing obviously with the material we're using is within their approved list.
Okay, now you got the question, so great. So Parisa was asking, would you please explain a bit more how you improve the characteristics of your char product? Which properties are significantly improved compared to normal biochar? So I guess what's the special thing?
We do. I mean, some of it is to do with particle size. So we do mill it to a specific particle size, which Jan did quite a lot of research on as to what particle size will maintain in suspension within the AD system, and that's one of the things that other biochars have suffered with. Sometimes you get sort of sinking or floating, and you sort of forms a cap on the surface. But what we want is to maintain it sort of evenly distributed throughout the tank. And the material itself is kind of a flaky material with it's a relatively large surface area, so to allow rough surface areas to allow the microbes to actually colonize it and form a biofilm on the surface of it. Like I say, we're not totally convinced about the diet aspect to it at the moment. I think that needs a lot more work to see if that actually is contributing significantly to its mode of action.
Yes, it's hard to look into the AD process itself.
Yes, it's a very dirty system, and it's you're kind of trying to pick out biochar, black biochar from a black liquid is not easy.
And another question from Allah was, what about the LCA of biochar in your system? Did you attempt to do an LCA already, or?
We're going to, because of the carbon credit market we're going into, we'll need to have an LCA around that. Essentially, I mean, the biochar will be going to soil. I mean, that's what will happen. I mean, it's basically through the AD system. It's almost like a little bit of a diversion, rather than just applying it directly to the soil. But we will do a full LCA around our production facility, our feedstocks, and the ultimate destination for the biochar.
Okay, great. Any more questions? Please be quick in writing them. Otherwise, if anyone is running a industrial AD site in the audience, please contact David.
Yes, we'd love to hear from people.
And other than this, yeah, thank you very much, David, for your presentation.